Hello. Hello. Good to see you. That's awesome. Good to see you. All right, let's see. Hello. Hello. All right. Hello, Michaela. Hello. Okay. Hey. All right. Wait. Oh, people coming. Oh, and a cat. Oh, we've got guests. This is awesome. Oh, wow. All right. I'm totally going to do the hello thing properly here. Hold on a second. That's great. We have guests. All right. Yes. Hello, Gabriel. Hello, Michaela. Hello, hey, Kameza. Hello, Rachel. Hiya, Kat. Oh, who is? Oh, yes, right. Hello, Lola. That is wow. Hello, Michaela's cat, who is named is something. That's awesome. Chima, you can unmute if you want, but all right, up to you. All right, but cool, very cool.
Professor, his name is Bongo.
Bongo, awesome. Okay, that is awesome. And I should totally have guessed that, maybe, or maybe not. Okay, that's awesome. I hope he's better behaved than my son will be when he joins. Hello, Jasmine. Hey, Jennifer, if I didn't say. Hello, Harry. That's awesome. Hi, Crystal. Hey, wow, I can't even. Hello, Johandri. Hello, Rahele. Um, Hello, Vanietta. I am good, thank you, because I'm about to teach my fourth favorite class. Hey, oh, okay, now I see. Hello, Michaela, and your cat. Yes, and hello, Bongo. I think you said Bongo, right? Okay. Hello. So, oh, yes, thank you. Yeah, happy Monday to you too, my God. Hello, Melanie. Oh, funny. Okay. I am a big fan of Bongo too. Oh, my God. Hello, Kellyanna. I got, oh, my God. All right, go for it. Go. Wow. Um, oh, now you even brought Kat out of her bad Wi-Fi situation. That tells you something. Okay. Oh my God, Miguela. Okay, everybody's killing everybody here. Whoa, there's another. Okay, that is crazy town. Yes. Those cats are breeding like rabid cats. Bootsy. Oh, I love the name. Hey, our next door neighbor's cat is named Bootsy also, and those are good names. And I don't know, they are very musical in nature, both of them. I always wondered if our neighbor's cat Bootsy was named after the bassist for Parliament Funkadelic and James Brown, but I never had the guts to ask. And I wonder if, wow, that's another one. Oh my God. Okay. Is the Bootsy cat is not named after, oh, it's not named after Bootsy Collins, is it? The cat? No, that would be, no. Okay. Fair enough. Why would that be? That's crazy. Okay. Oh, wait. There seems to be a trend in those names that has something to do with the letter B, but I'm not gonna. Oh, now you got
The hair of that one is amazing on his head, his markings
well, this is oh boom.
or
Okay.
her markings.
Wow, you're all way. Yes, I like the markings too, but I'm stuck on the names here. I'm okay. I hate every time I think I'm cool for like a minute. Every time I think I'm with you, people, there's always like a reference that shows that I'm totally out of touch. See, but I barely even understand the word avatar, let alone who. Okay, you're way ahead of me. Now I'm outclassed. Oh, and you were right, apparently. Okay. Oh, wait, what is going on here? Okay. No, that is very cool. Anybody else who has animal? Well, I know it's now like a thing that, um, sorry. Okay. Yeah, and now it's like a thing that people, Bowser, I like that name. Okay. That reference, okay, I have associations with the name. When I think of Bowser, I think of two things. One, the lead singer of a group that used to be called or what used to be a group called Sha Na Na, which maybe nobody cares about anymore. But also, I think of the Bowser of like from Mario and all that. But I don't know if that's the Bowser that you mean. But or either of those Bowsers. But okay, those are cool. Oh, cool. All right, so at least I get that. Thank you for making me feel a little bit less out of okay, that Bowser I get. Um, okay, very cool. So we're gonna start. Yes, this class. I'm so glad that it's this class that I have at the end of a Monday because I don't think I could bear any other class at this hour, especially not for 2.5 hours. So thank you for making this human as usual. All right, let's get some business here. I still owe a couple of people things. That's I now have to admit I totally forgot that was the case until like 2 minutes before this class. So I apologize. You know who you are. If you are a certain individual that I owe something to, you might even feel free. I can't do anything about it in the middle of this class, but if I still owe you something large, feel free to text me a gentle reminder or request. Like it's, because I have to admit, I forgot that was the case until right now. So you know who you are. If I owe you something, it's not your fault, it's my fault. You can feel free, but you deserve it. So feel free to send me a text if that would help. Or anyway, but now for most of us, for all of us, what I was just reminded earlier today, tell me if I'm wrong about this. My understanding is we have class a week from today, and that's it. Like, I think we do have one more class after today. Yes. Okay. Thank you. Okay. And I think that also means so you have today with me, and that doesn't shock. I mean, that actually is not a shock. I mean, I shouldn't be shocked by that. And it is all sort of part of the way the clock works. But yes, so you have me today. You have me again a week from today. That's like 5 hours of me. So we got plenty of time to finish anything. But then you've got Walters this Wednesday, and that's it for Walters, right? I mean, you've got like, yeah, I guess you just confirmed that. Yes. Okay. Thank you. And the last is bonsai. I thought, okay, so the last cat is bonsai. I thought for a second you were saying the last day of classes is bonsai, and I had no idea what that meant. Okay, the last cat is, for all I know, that's another Mario character that I don't know, but Monday is the last day of classes, right? Okay, that is my impression as well. So, so it's time to start, tying up loose ends and preparing for the final. One thing that there's a couple of things I put in your stream. One thing I put in last week that we didn't even do, there's a certain quote, just a quotation that I put, it's called Letter to Bentley or something, which I did put in your stream last time. We didn't get to deal with last time. We're totally going to deal with it today, if that rings a bell. So you may want to look or sort of have it ready. Again, it's just a very short, small document, like not even 1 page long, that's called Letter to Bentley, I believe. And it's to, please just like have that at the ready or somewhere on your screen or something, or have access to, because we're going to deal with that in a big way in a few minutes. But also something I just put in your stream, or whatever you call it, today, like about an hour ago, is something that I think I called the pre-final, or I should call the rough draft of the final. This is as part of our arrangement or our deal. Now that we're getting closer, like let me just remind you that, yes, again, when you have a final exam in this class, I mean, you will have a final exam in this class. It will be arranged the way your midterm was. That is, the actual official, real final exam will be posted probably next Monday night, right after we finish class. Probably the actual thing itself, that you will have essentially a week to turn around. Like, it will basically be due 11:59 p.m. on Tuesday the 25th, I believe. Correct me if I'm wrong, but I believe Tuesday the 25th is the last day of the final exam period. So you'll essentially have to that night to turn in this exam, which is kind of stupid on my part, but I believe that's right. So you'll have the week to do it. You'll be able to talk to each other, go on the web, yada, yada, yada. That's the actual document. So you'll have a week to do the actual thing that will actually be posted essentially a week from today. But what I just put in your stream is the rough draft of that. I mean, essentially, it will look like your final exam will more or less be what I just put in your stream. I say more or less because I'm sure I say more or less for a couple of reasons. One, I'm sure I will find errors that I'll have to correct before then, or we'll shave some things down to make it more perfect for your class. It won't get longer, but it might get shorter in places. We'll update it and tweak it as we go. Also Walters's part will definitely be updated and tweaked. Like, you're not going to have the exact same Walters questions as are in there right now. But basically what your final exam will basically be an updated draft version of what you now have in your possession. You'll also notice that what you have in your possession right now, and we're not going to spend this whole period talking about it, but we're going to talk about aspects of it. you'll notice that what you have in your possession actually has walkthrough solutions in it. I mean, it has answers in it, I believe, for a lot of it, maybe not all of it, but a lot of it. That is also, that's good. That's intentional. Like, we want you to have that. And we will walk through some of those with you. Like Walter's will in his last class Wednesday. I'm going to talk again with him. We'll make sure of this. And I will answer questions and walk through parts of it with you, or if not all of it with you, next Monday. So any advanced preparation you do or any studying will be to your benefit. Any ways in which you can bring things to my attention by next Monday will be to your benefit. But along the way, I'm sure we will find errors, possibly even in the solutions. Like, that does happen. So please know that's not the final story. There will be updates, there will be revisions, and any updates you get, you gotta, keep up and throw out the old and keep the new. But basically, that's your sneak peek. I mean, basically, that's your practice exam for the actual final. And it's only not the final to the extent that we have to fix it and tweak it and make it perfect for your final. But basically, that's it. And basically, you're going to spend a lot of time on Wednesday with Walters, I believe, walking through it. And he'll explain to you how the test works and what the questions mean and how to answer them and stuff like that. And then when you see me on Monday of next week, really, hopefully by then, your questions for me will be super specific. Like, you'll already hopefully feel very comfortable with the basic document. And then, it's time for the final looks at the final then. So, but that's a long way of saying, like, there should be we don't want there to be any surprises. By the time the actual final exam is posted, essentially a week from tonight, it's going to look very, very, very much like what you have there. Oh, okay. And again, let me say this too. Again, Walters will be more thorough about this with you, but I'm saying it's just like the midterm in these important respects. It's just like the midterm in that it's a take-home document that is not expected to have test conditions associated with it. Like, just like the midterm, you can take as long as you want with it. You can walk back and forth to it. You can use other resources, certainly including your class notes, God forbid, certainly including go and look at videos from the class to find things out, certainly including talking with one another, but also including the web and Chegg and stuff like that, if you dare. In that respect, it's all like the midterm, that we are not enforcing test conditions. And we'll grade it like the same kind of way. And we want, a beautiful final copy that has like colors and clarity and that makes all the questions clear and all that. However, you will notice one thing is different about, like, the format for our final exam is a little bit specialized and a little bit kind of, maybe you could say, funny. It's ultimately actually meant to make things very easy for you. The final exam is designed to kind of force us all to put all the course material together and see what the purpose of the course was, or like why we took it. And again, like, Walters will be more thorough about this on Wednesday, but you will notice that basically in the exam, we have a bunch of, and you can look at it now or not, but there are some funny things about the instructions, I guess is what I'm saying. The instructions themselves are a little bit unusual and a little bit different from the midterm. They're not meant to be a shock. That's why we're giving them to you now. And it's why we're going to explain them, but they are a little bit different from the midterm and a little bit unusual. Basically what happens is, I mean, the short version of this, and depending on how far we get today, I could say a lot more about it, but basically what you'll notice is that you have, like, in part one, you have a bunch of little scenarios that are essentially true-false questions. They're true-false like scenarios. I forget exactly how many we gave you, but in part one, we describe a little scenario and we ask you to say whether it's true or false, by which we really mean we're asking to say, could this have happened or not? Maybe in a minute I should turn to it, but I'm just afraid to get too bogged down in this right now. But in part one, you read a little paragraph and then you're just asked to say true or false, meaning like, as the paragraph explained things, could that have actually happened? Like if this person got that number, if it was a Doppler effect situation and, this person measured this frequency and that person measured that frequency, like, but this person was moving that way and this person was not, or something. Is that the way it would actually go in real life? We're asking you to read each scenario, and according to the physics that we've learned here, just say true or false. And in your first pass through, that's all you do is you literally just say true or false for each one. Then in the next, then we take the same scenarios, like in part 2 of the exam, you go through and you look at those same scenarios. And now we give you a little question like in part 1, if you said it's true, then solve for this number. If you said it was false, then solve for this number, right? So then it's like a little computation that you do based on that exact same information. So in other words, if it's true, you just do the computation. But if it was like false, then you have to like solve for a number to make it true, kind of thing. So you go through these scenarios and first you say each one, whether it's true or false. Then you do a little computation to kind of make the numbers work and show that you understand the numbers for each scenario. Then we ask you to put this, oh, is this a question? Oh, sorry. Wait, sorry. Oh, sorry. Oh, cool. Oh, cool. Okay. I think okay. Sorry. So first we ask you to go true or false on each scenario. And by the way, if there's any particular scenario there that we all know for a fact, by next week, if there's any scenario in there that we know we've never covered this year, because like we're all in COVID and it's all a nightmare and all we do is talk about video games, whatever, then we'll know that and we'll take the scenario out. Like, believe me, you're being tested on what we taught and learned. You're not being tested on like some objective curriculum that came down from Moses or something like that. So if you happen, and we still have some time to teach you some things, right? But if by next Monday, there's some scenarios in there that look totally unfamiliar, and you're like, what is this? This has nothing to do with anything we ever, then we know that, and it won't be on your final, like trust me on that, like, believe me. But anyway, first you go through and you say true or false on each scenario. Then on the next pass through, you do some numerical calculation that we ask you to do so that you can sort of make each scenario realistic. Then on the third pass through, then we say, put these scenarios in an order. Like we actually ask you to, sorry. Then on the third pass through, we ask you to write down a sentence of English, basically capturing the concept illustrated by that scenario. And again, Walters will talk more about that. I'll try to talk more about that, but we're asking you then to back off the numbers and back off the details and just like declare to us or declare to yourself, what is the finding? Like essentially, what's the motion? What is the conceptual claim that has been advanced by that scenario or that is being demonstrated by that scenario? So first you say true or false. And so in each one, even if the scenario is false, it's still like illustrating something. It just might be doing it with numbers that don't work. So first you say true or false, then you do the numbers. Then you say, okay, this one is illustrating that all waves travel at a speed fixed by their medium, something like that. Then we ask you to put the scenarios in an order, meaning essentially the order in which we learned them in class, but more to the point, you're putting them in an order that logically makes sense. Like you first learned simple harmonic motion in this class, then you learned wave motion, not just because that's like the order that would be in the textbook, but because waves don't make any sense without simple harmonic motion. Like waves are based on some, as you know, like wave motion is simple harmonic motion happening in both space and time. So we ask you to put those motions in the order that logically is necessary for them to make any sense, okay? And then in the final thing of the whole thing, we we ask you to put it all together and come to a conclusion. And I'm saying final, I mean, I might be saying the order of the exam, the exam might go in a slightly different order from what I just said now that I'm thinking about it. But basically any of the funny instructions, that's what they are. And it may all sound very, I don't know what it sounds like, but for the most part, any hard calculations you're doing in the exam or any involved calculations are basically all about the Doppler effect. You might notice that too if you're looking at the exam. I mean, we do sort of make you run through a Doppler effect problem as well because we've been talking about it for so long and because kind of it puts together everything from the course. So I think that's in there too. But even if the whole thing looks very long, what I think I'm trying to say is that for the most part, you're in the exam, you're just kind of running through one particular list of things sort of over and over again to try to put together the whole course. And putting together the whole course is kind of my job to you now for today and next Monday. And we're almost there. I mean, we are just about at the end of putting all the material together. And I've mentioned before, when I say putting together the whole course, what I really, really mean, so I'll say this again right now, and then I'll circle back to it. The punchline of this course, like if you actually get everything we're doing and you take the final exam and you do well on it, and what we're hoping you'll see by the time you take the whole final exam, or by the time you practice for the final exam, what we want you to see by the end of this course is why why physicists believe that the universe is expanding. Well, let me say two things about it. We want you to see three things. We want you, one, to see why people think that, like in other words, why that's a logical belief. Two, we kind of want you to appreciate the weirdness of that belief. So maybe I should say that in the opposite order. I mean, I think you all know, I think you've read enough newspapers or have been enough, you've lived in the world enough that you've heard that the universe is expanding. And you've probably also heard, I'm sure you've heard of the Big Bang. One thing you may or may not realize, I'll just say this right now, is that the two concepts are very intimately tied together. Like once anybody has any reason to believe that the universe is always expanding, like if you believe that as time marches on, the universe spreads out like this, then it does stand to reason that if you're picturing the mental movie, if you have a mental movie of a universe going like this, if you ran that movie backwards, you would see the universe going like this. In other words, if you believe the universe is getting bigger and bigger all the time, it sort of stands to reason that if you just considered what the beginning of the universe would have to be like, according to that movie, it would be super small and it would have exploded out. So like once we believe in an expanding universe, it's not a shock that we believe in something like what we call a Big Bang, right? Okay, so people have heard of this their whole lives, I guess. But what we want you to see is sort of two things. I mean, this is always the thing in physics. One, we actually want you to appreciate, and I'm going to deal with this today and Monday. I want you to appreciate that even if you've heard your whole life that the universe is expanding, like that's a really weird idea. That's a really weird idea. Like as usual in physics, yes, I want to convince you of it by the end of this class, and next, like by the end of this course. I want to convince you of why it's reasonable to believe in an expanding universe. But even before I do that, I actually first want to convince you that it's not really reasonable to believe in that. Like it's not a natural thing to believe at all. It may be logical based on all this physics that we're doing together. Hopefully, it may be logical based on all the physics that we're trying to expose you to. It is logical based on the physics we're trying to expose you to. That doesn't mean it's reasonable. Like, in fact, I guess to put it another way, if we really do our job in this class and you really do your job in this class, then by the end of the class, you should really actually think two things. One, you should think that due to all this other physics that hopefully makes sense, that it makes sense to believe in an expanding universe. But you should also think that without all of this physics, or other than all this physics, or but for all this physics, no one should ever believe in an expanding universe. Like you should only believe in it because of all this physics, because in and of itself, it's a crazy idea. I mean, and I think someone at least maybe is nodding. Thank you. I totally appreciate it. And I'll just quickly say why it's so I'm not trying to confuse you, but really to me, the delightful thing of physics is always this kind of confusion. Like everything I like about physics is something that is surprising that I wouldn't have expected and I wouldn't think is natural. But then if I think about it hard enough, it actually does make sense. Like if it weren't for both of those happening at the same time, I don't know why I would think physics is exciting. Like it's exciting because it is a surprise that somehow makes sense, I think. So the expanding universe, which I'll get like wait, am I getting myself too? So, okay, I am getting myself too far afield. Like the punchline of the course is we believe in an expanding universe for reasons that actually make sense when you go motion by motion, step by step through the material of this course. And that's what the final exam is sort of designed to get you to see that you see. Okay. And so if you just have that in the back of your mind through today, through next Monday, that it's all about putting all these ideas together to see how they fit to make one big argument or one big like long argument. Like if this whole thing, we were in court, right? The whole idea is we've put now a series of pieces of evidence or a series of motions on the table, and we've put them in a particular order because you need the first one in order to believe the second one, and you believe that you need the second one in order to believe the third one. But by the time you get to the end, it's like one long argument or one long derivation or one long proof for an ultimate conclusion that says the universe is expanding. That's supposed to be the idea. If you have that in the back of your mind when you look at the stuff, it hopefully would help you study or help you understand the final exam document. I will be more specific talking through it if I can, like once I finish the material that we're actually doing today, but also that's what Walters will do on Wednesday. So hopefully that makes any sense at all. Oh, yeah. Okay, I'm sorry. So question in the direct chat, I'm totally psyched about. So I won't say the name because it's direct chat, but someone is saying in the direct chat, can we still ask for help like we did for the midterm? So yes, well, depending on what you mean. Number one, absolutely. Like one of the reasons that I'm putting this document in the stream now, even though again, as long as you guys all understand that it is subject to revisions and updates, but yes, absolutely. The more you look at that document in advance, whether it's at the questions or at the answers, you're absolutely encouraged to ask for help or assistance. I mean, particularly in class, like today, Wednesday with Walters, and Monday next week, definitely you can. Now, if you're also asking, because this did come up a little bit last time, once we actually post the thing, so I don't know if this is what so yes, totally. And again, we're not trying to fool you. So you can assume that your final exam basically looks like this thing in the stream. And yes, you can totally ask us about this thing. And not only in class, I mean, you know, you can text and email and stuff like that as well, you know, throughout this week. To be clear or to be explicit, let me say though, once we post the actual thing, sorry, I'm just thinking about dates. Once we post the actual thing, like next Monday night or whatever, and then you have the finals exam week to do it, like the 17th through the 18th through the 25th, then during that time, once it's out and it's final exam week, you can still help each other, and we hope you do. But I'm not sure how I'm going to answer questions or give help during that time once it's actually happening. I mean, you know, if it's a clarification or you think there's an error or something, it's not like I'm going to shut down my phone and I won't answer texts or something. Like I will take texts, but I will be a judge of whether I can answer the question in text or not. Like if someone's and this did happen, I don't think it was this class. I think it was another class actually, but yeah, I do have to sort of draw the line. And I can't really hold your hand or I can't really give advice or guidance once the test is going on, especially if you're already allowed to talk to each other, stuff like that. Just because then if I start giving guidance to one person more than other people, that gets a little bit sketchy. But also and also I kind of think at that point, like, come on, you know, we're giving you enough resources that we hope you could figure it out by that point. But also just to be super realistic and super honest, by the time it's final exam week and all of you are doing all these finals, they're all going to come in at the same time to me on that last day of finals. And somehow which is like the really stupid part of what I'm doing. And I'm regretting it even as I say it. But on that Tuesday, that 25th, like your exam is going to come into me and the exams from all the other classes. And I'm going to have to turn around all of them and get all my grades in like pronto, which is, as you can imagine, frequently an issue for me. So what I'm going to be doing during the week that you're scrambling on your exam is I'm going to be scrambling to put everything in order so that there's as little as possible to do with your grades once they come in. So basically, I'm going to be frantic that week, and I would rather not be actually helping people with their exam while they're taking it, because then I'll never get your grade. Then you'll never get your grades. So I don't know if that's clear or not, but yes, you could definitely ask for help all the way up until next Monday. And again, anything you ask for help with about this document will be very relevant and helpful to you for your actual exam. Okay, so when's the final? So I'm saying, and I know I have to put this in the stream, but basically I'm saying your final exam will be posted probably late night a week from today, maybe the next, yeah, this is actually getting crunchy for all of us. I have to get back to you, and I have to talk to Walter. Like, we'll have final confirmation for you this Wednesday when you have Walter's. But basically, roughly, I'm saying your final exam will be posted late night a week from today, like after you've already had class a week from today, Monday the 18th. And it'll be due back, Monday the 17th. And it'll be due back probably 11:59 p.m. on Tuesday the 25th. If that's answer. And so does that answer? I mean, that's not exact. We'll give you the exact final thing Wednesday from Walters, but oh, okay, cool. But that's basically the idea. Okay. And the reason I keep pausing is I keep realizing, like, that is right. When it's what I want to be right, but I realize that all day I've been saying that to every single one of my classes, and now I'm realizing why we always used to put different final exams on different days, because this is going to be kind of crazy. I'm definitely doing something wrong doing it this way. But yeah, so let Walters give you the final exact confirmation of that on Wednesday, but that's basically the idea. Okay. But thank you for the thanks. Thank you I love it when people acknowledge that I did actually address their question. Okay. Now I want to get to the material. I want to try to wrap up this material for you, today and next Monday. And I think I know where we all are. And I want to do it largely through this quote that I put in your boxes. There's a reason I put this quote in your boxes last time, but let me ask before we go any further, or let me confirm. Last time we met, you had just started doing circuits with Walters in simulation lab time. And I believe, can I confirm, I believe you did more circuits. Yes, you did. Okay, thank you. All right, so you're deep in circuits now with Walters. Like, that's where you are, right? Like, that's what's happening in life with Walters is circuits. Yeah. Okay, cool. That's good. That's as it should be. Okay. So then then give me a second too. That brings me to, hold on. Okay. So, let me look in the chat. I'm sorry. Oh yeah. Okay. Correct. Okay, cool. Thank you, all three of you, or all four of you. Thank you. I appreciate it. Okay. So, right. So I'm just flipping through I'm using the same note packet as we used last time. And obviously this all is a PDF that's in your notes from the stream, but I'll upload this again once we add more notes to it. But right, so last time we talked about all this, yes. Okay, right. This is what I was hoping, this is what I thought. So where we left off last time was this page. What I'm going to do right now, since I got all excited and wrote all over the page in red and makes it totally legible, I'm just going to sort of recopy the content of this on the very next page and pick up from there. So I'm saying this. Okay. So premise. So now, and I know in Walter's context, you're dealing with these circuits. You're dealing with the flow of charge. Charge is flowing through a wire. It's going through resistors, and it's coming back to the battery from which it came. And the whole premise underneath. So you're dealing with the particular, and that's what lab is for. You're dealing with the particularities of Ohm's law of current equals potential difference over resistance, and you're dealing with series and parallel and all the stuff that I won't repeat right now, or I mean, but that you're responsible for, but I'm assuming you're getting from there. But what I'm here to reinforce or emphasize is like why all that's happening in the first place. Like, right, like why electrons are running from one terminal of a battery back to the other terminal of the battery once they're given the opportunity, is because they're attracted, right? The electrons over here are attracted to the protons over there. Also, the electrons over here are repelled by the other electrons over here. And that attraction or that repulsion happens mathematically the exact same way that the Earth is attracted to the sun, or the sun is attracted to the Earth gravitationally, or a brick is attracted to the center of the Earth, like, or any object that I hold near the center of the Earth. Like, in other words, according to gravity, any one mass in the universe is automatically pulling on any and every other mass in the universe all the time, with a certain strength that is greater, the greater either or both of the two masses are, and with a force that's greater the closer either of the two masses are, right? Oh, and I should say, I'm sorry. I'm going to flip the page in a second, so let me just summarize. So, I mean, this is sort of obvious, but you know, M1 and M. Okay. M1 and M2 are 2 point masses. Q1 and Q2 are 2 point charges. They're arbitrarily designated, but we generally make one look big and the other look small, because if it's arbitrary, if we're talking about any two objects in the world, I mean, it's possible that they're both the same size, but it's more likely that if they're just randomly chosen, that they're not the same size. So whichever one is the bigger one, we just designate as number one and give it a big letter. And whichever one is smaller, we designate number two. But then what we end up doing is calling the bigger one the source, whether we're talking about gravity or electrostatics. Whichever is the bigger one, we end up calling the source. You'll see why soon. And the other one we end up calling the test. So the idea is, say we're talking about gravity for a second, like M1 could be the sun and M2 is the earth. And then the discussion that we would have, or the thing that we would be talking about, is how the sun is pulling on the earth. Now multiplication is commutative, and Newton's third law is true. Like if I pull you, you pull me back automatically. So if I'm talking about the sun pulling the earth, it's also absolutely equally true that the earth is pulling on the sun, and with the exact same magnitude of force. However, I want to focus on one, I want to know which one I'm focusing on and what I'm saying about it. So just as a way of discussing, or just as a convention, whichever one you make the bigger one, whichever one you call M1, that means you're discussing it as the puller, as the source of gravitation. And the other one that you make like little m2, we discuss that as the pull E, the thing being pulled, and it's called the test mass. Okay, same thing with charges. So we have a source charge and we have a test charge. The source charge is the one that pushes or pulls the other one, and the other one like receives. And again, we can always flip around and talk about it the other way whenever that's relevant. All right, so that's just what those symbols mean. But then on the next page, just to be clear, in both cases, well, hello. Okay, just to be clear too, and I know you know this, I think, but we use R, whereas some people you could use D to mean distance, but for reasons that have to do with radius and orbits and stuff like that, we use R to stand for the distance between the two objects in question, whether it's 2 point masses and we're talking about gravity, or 2 point charges and we're talking about electricity. And R stands for distance, but specifically really what it is the magnitude of a displacement vector. Like there's really an R vector that has magnitude and direction. R vector would be an arrow that points from the source to the test, like by convention. Okay, and R is the magnitude of that displacement vector. So R is the distance of the displacement vector. So in other words, we actually do track both the separation between the two objects and the orientation of the two objects. And in our convention, the way we track orientation is we draw a line in our mind pointing from the source to the test, like as opposed to the other way around. And then also, okay, this gets a little technical at the bottom. Oh, hello, I just lost everybody in the world. Hold on a second. Okay. I know some of this I said last time, but just to put this in perspective, like the main thing I'm trying to do right now conceptually is show you that the equation, the relationship between masses gravitationally is identical in mathematical form to the interaction between charges. I'm trying to show you that the that the mathematics of the force is the same in both cases. It's only just like the size and the scale and the numbers that differ. So in each case of the gravitational interaction versus the electrostatic interaction, in each case, the bigger the object, the bigger either or both of the objects, the bigger the whole force. The closer the objects, the bigger the whole force, right? Because R is in the denominator. But in both cases, the closer the objects, the bigger the whole force. But for some reason, in this inverse R squared way, like I will discuss that, but just no, like for a reason there is a reason. It's not obvious yet. But in both the case of gravity and electrostatics, the closer things are, the harder they pull, but not in the most direct, obvious way. It's not just an inverse proportion, it's an inverse squared proportion. I want you to see that similarity between the two forces. And then the two forces have a constant of proportionality in them. One has a big capital G, the other has a big capital K with a sub E. They are just universal constants that can be measured in the lab with something called a torsion balance. They are constants in that they are universal. They never change, but they're different from each other. So, and you don't have to memorize them, but you can memorize them because they're never going to change. But just look at the unit, and they're there partly just to make units work out. Like they're there to make we want all forces to be measured in newtons in the end. A newton is a kilogram times a meter per second squared, right? So the units of these things may look very funky when you look at them at first. Like the units of the gravitational constant are newtons times meters squared divided by kilograms squared. That sounds like quite a mouthful. But if you think about it and you just relate it back to the equation, oh, I'm starting to write things in the reverse order, sorry. But like if you look at the gravitation equation at the bottom of the sheet, capital G is measured in newtons times meters squared divided by kilograms squared for the very direct, not coincidental reason that makes the kilogram squared in the denominator cancel out with the kilogram squared in the numerator. Like you have mass times mass. So kilograms times kilograms. So those kilograms cancel out with the kilogram squared in the denominator of G. And you have meters squared in the bottom of this whole equation. So they cancel out with the meters squared in G. And then what you're left with is newtons. Like G, in other words, the whole G constant is just a constant that ensures that our answer is left in newtons. If we didn't care about the metric system, if we were willing to measure things in more appropriately scaled units, we wouldn't even need the G at all. And then same thing with the K. The K is measured in newtons in units of newtons meters squared per coulomb squared. So the coulombs in the top cancel out, the meters in the bottom cancel out, and you're left with newtons. Okay, so this is all to say that there are these two forces in the universe, one force that seems to exist between charges and one force that seems to exist between masses. Both forces are measured in newtons. Both forces do what all forces do, which is they go into the left side of F net equals ma. Like they push and pull on masses so that the masses end up being accelerated at a certain rate, right? So, and yeah, and a coulomb is a unit of charge. We discussed this last time, such that, I mean, the coulomb is a unit of charge such that one of these units of charge flying past you in every 1 second gives you what's called an ampere of current in the lab, right? But just for perspective, again, 1 coulomb of charge is a lot. It's, you know, 1 electron itself has like billion, trillion, I was going to quadrillion, quintillion, right? So 1 electron, I mean, it takes like 16 quintillion electrons to make 1 coulomb of charge. It's a very big number of electrons, but and that's how much it takes to get 1 full ampere of current. But that's all just like unit conversion and all about the scaling of these things. In the end, each of these forces is a force measured in newtons. And each of these forces is an inverse R squared. Okay, so okay. Oh, chat. Sorry. Hold on. Okay. Now I'm talking about these both forces. Like your main thrust right now in the class is electricity, the flow of charges. But I want to discuss electricity in the same breath. Okay. I want to discuss electricity in the same breath as I'm discussing gravitation, partly because gravitation is the more common familiar phenomenon. Like it's a little bit easier to picture things falling toward the surface of the earth than it is to picture like electrons like flying around toward protons. So anything that we believe about one, we believe about the other. So it's sometimes easier to discuss them both at the same time. And we believe in gravity because it happens all the time. But now I want to really investigate an aspect of both of them. Like on the one hand, they both have this weird inverse R squared form, which we get used to. On the one hand, they both of the electrostatic interaction and the gravitational interaction have this sort of strange mathematical form, which is worth unpacking. But they also have this property that is that they are what we call action at a distance. Like, let me back up for a second and say, remember, all forces are interactions. All, like force by definition means interaction. Okay, just to remind you again, and this comes up in physics a lot, like a force is not ever something that an object has. A force is always something that an object does to another object. A force necessarily is an interaction between two concrete objects. And gravity and electrostatics are not the only forces that we've ever discussed in our life. Like we've discussed the spring force. The spring pulls on a mass. And by Newton's third law, by the way, the mass presumably pulls back on the spring, although we don't often care about that in like all the contexts that we've done. Or back in physics 101 or physics 1, wherever you took it, like a surface can exert a normal force on another surface. or a surface can exert a frictional force on another surface, or a string can exert a tension force on a fish or something, right? Forces are always interactions between two objects, and we know about many, many forces, like in the context of physics. However, there's this one so the fact that gravity is an interaction and that the Coulomb force or the electrostatic force is an interaction, that itself is not, that's not what makes them fundamental or important or inverse R squared or weird or anything like that. Forces are always interactions. What's interesting about the gravitational force and the electrostatic force is that they seem to happen without touching, right? Gravity, yeah, no matter what force we're ever talking about, the point of a force, like for all forces, sorry. No matter what force we're ever talking about, the whole point of forces is that once you know all the forces acting on an object, no matter how many there are, you add them all up, and the sum of all those forces on each individual axis of space will produce the acceleration of the object along that axis of space. Like the point of forces is that you add them up and they produce accelerations, F net equals ma. And that is true for any force we're ever talking about. The consequence of a force is acceleration. But mostly the way we identify forces and the way that we recognize them and the way that we know how to put them in a free body diagram and then break up them into vector components and then do F net equals ma, mostly what we look for is physical contact. Like we know that the tension of a string is pulling on a fish if the string is touching the fish. Or we know that the normal force of the desk is supporting the coffee cup on the desk because the desk is touching the coffee cup, and vice versa. What's strange about gravity is that we have this belief that the Earth can somehow gravitationally pull on objects near its surface without touching those objects. Like I lift this thing up here and we believe the center of Earth is pulling on this thing up here, even though there's nothing between this object and the center of Earth. Or even worse, not only do we believe that gravity can pull on my pen right now, not only do I believe that the center of Earth somehow is pulling on my pen without touching the pen, but I also apparently believe that even if I put something in between the pen and the center of Earth, that would still happen. And even if I put a lot, like even if I support the pen on a desk, we don't believe that gravity is going away. We just believe that now the desk is exerting an upward force to counteract the effect of gravity and thereby make the net force on my pen zero so it doesn't accelerate. But in other words, we seem to believe that the center of Earth is always pulling on my pen regardless of what's going on in between, that Earth doesn't have to touch my pen, nor can it be blocked by anything in between it and my pen. We believe that we believe that objects apparently can exert gravitational pulls without any physical contact, without touching, through empty space at a distance. we also believe this about protons and electrons. Now let's just talk. Oh, sorry, someone's here. Hold on. Now it's weird enough to believe. It's really weird when we start thinking about protons and electrons, and it would be very hard for me to actually convince you logically, like why we should believe it about protons and electrons, unless we see the effect on protons and electrons. And it's kind of hard to see the effects on protons and electrons unless you like group a bunch of them together and send them flying through a wire, which it took us till the 1800s to be able to, or the late 1700s to even be able to do. So first and foremost, why you're doing all these circuits in lab, like why we care about circuits so much is it's really the most vivid or most believable demonstration of anything we could ever say about protons and electrons in the first place, which are very hard to see and picture. They're so small. So while we're talking about all this electricity thing, let's also relate it back to gravity. With gravity, we believe that like the sun is pulling on the earth without touching it at all. And we believe that the earth is pulling on objects without touching them at all. Now that's a weird thing to believe. It's a very weird thing to believe. On the one hand, it's hard not to believe in gravity because it seems to be happening all the time. Like yeah, things fall to the earth all the time, but and we can even make really good numerical predictions of exactly what rate they're going to fall. And we can even ultimately say, as Newton did, that the way in which things fall to the center of the earth ultimately comes from the same explanation or the same phenomenon and the same mathematics as to why the earth itself is falling toward or around or whatever the sun, right? And this is what Newton's saying in his law of universal gravitation. He's ultimately saying, look, we got all this data from stuff falling on Earth. Like we could do all these experiments now. Galileo started us off, and we did all these experiments on inclined planes and with pendulums and so forth, watching things accelerate towards the center of Earth. And then we got all this other data from like Kepler and Copernicus and all that Newton puts together. And we look at all this data in outer space, things moving, falling, spinning in outer space. And Newton puts it all together and says, I think it's all one and the same phenomenon. I think it is in heaven as it is on earth. I think that no matter whether you're a mass over here or a mass over there, evidently all masses are pulling on each other in this precise numerical way at GMM over R squared. And we can run the numbers and see that the solar system data lines up with this, just like the terrestrial data lines up with this. And it looks like we've got this one sweeping explanation to describe all of these motions. And we call that sweeping explanation gravity. And at the heart of the gravitational theory is this idea that every single mass M1 in the universe is automatically and necessarily and perpetually pulling on every other mass M2 in the universe without trying to at all, without needing to be particularly near it or particularly in contact with it. Like if you just look at, like, the equation is not that hard mathematically, but it is quite a big claim. Sorry. Both of these claims, but if you look at the gravitation one at the bottom, it is saying for any two mass points you pick, the sun and the earth, or the earth and the moon, or the earth and a brick and another brick, or a brick and a piece of dust in the Andromeda galaxy, whatever. The gravity statement is saying any two mass points you pick, without having to try or without having to do anything or meet any particular conditions, they're just automatically pulling on each other through empty space, or equally through any barriers that you might want to try to put between them. And equally, we're saying any proton and any electron are automatically pulling each other through empty space with a numerical amount that we can verify, with a numerical amount that we can predict and then verify in the lab. And similarly, by the way, any proton and any other proton are pushing each other through empty space. Now, Newton didn't know about the electricity one. Newton came first, and then Coulomb came like about 150 years later, but with the exact same mathematical format and not coincidentally. And Newton believed, Newton gave us this law that we still use today to put men on the moon, for example, to send rockets to the moon and stuff. Like, we believe it, and to predict orbits and eclipses and all of that. We believe this law for the same reason Newton believed this law, which is that it works. The numbers work. The predictions are correct. I mean, to a certain degree, to a certain number of significant digits. And we believe Coulomb's law because it works, because it makes predictions that ultimately allow for circuits, which totally work and ultimately like turn on light bulbs and stuff and do everything. But it's a weird idea. The idea that when we say it works, we're saying we think things are pulling and pushing each other through empty space. I want to specifically take a moment to show you how weird that idea really is. Like, I'm not saying it's wrong, but I'm saying it's weird. Okay, so let's look at this. Oh yeah, no, thank you. Oh, okay, wait. So there's two things in the chat. I'm sorry. So one thing about predicting eclipses, and I don't want to get. That's a great question, and I don't want to get too. Maybe it was too loaded of an example for me to just throw in casually like that. But let me. What I can say for the moment is this. The gravitational statement, GMM over R squared, is supposed to apply it's supposed to apply to all masses in the universe. So it applies not only, it applies to stars and planets and moons as much as it does to anything else. And in fact, it really, the way he got that equation was from a bunch of data that had been collected by Kepler, by Copernicus, and I'll address that. There's also something in the private chat about Copernicus I totally agree with. I'll try to address that in a minute. But yeah, Copernicus was awesome. And yeah, totally awesome. Yes, and total credit to Poland without a doubt. And I'm 1/4 Polish. But wait, eclipses. But yeah, so GMM over R squared comes from astronomical data, and then it helps us predict astronomical data. Eclipses, yeah. So I have to try to say this without going too far afield, but an eclipse occurs when there's a certain arrangement between three bodies. Like, in other words, a total lunar eclipse, from our standpoint, we'll have a total lunar eclipse. We have a total blocking of the moon when we are directly in between the sun and the moon, when the moon is totally in our shadow, you might say, right? So a total lunar eclipse happens. I mean, the moon goes around us. Yeah, if I'm not careful, I'll get really, because I love this stuff. I want to try to keep myself linear here, but the moon takes a month to go around us. And every single month, I mean, every 29 and a half days, for sure, we'll find ourselves in an arrangement where the sun, I'm trying to do this on the screen correctly. Hold on a second. I mean, it only takes 29 and a half days for the moon to go fully around us. So like every 29 and a half days, if I get so disoriented with this screen, if this is the sun and this is the moon, I can't, every 29 and a half days, the moon will end up over here where the earth is right in the middle. Only usually the earth will be somewhat above or somewhat below. So every 29 and a half days, we have a full moon, but we don't always have an eclipse because the moon isn't always right along this axis. But whenever the moon is in this axis, we not only have a full moon, but we have a lunar eclipse. But all of these are cycles of motion. In fact, they're cycles, much like simple harmonic oscillation is a cycle. And all of these cycles are totally regular and very, very predictable. And predictable with data that we had even before Newton, we've had for hundreds and thousands of years. And in fact, the data is so good that even when we all believed that the earth was at the center of the universe and that everything was going around us, the data still worked. And so we can predict eclipses just in the same way that you can predict like how much time will it take until the mass on the end of a spring is all the way over here again. It's just like predicting periods of oscillation. That actually is what's going on when we predict eclipses. We're in effect predicting periods of oscillation, only sort of in 2 dimensions or 3 rather than 1. So I mean, I can't get too far afield in it, but it is very predictable, and the predictions are made much easier by certain equations such as GMM over R squared. Also, here's a little plug. If you really want to know about predicting eclipses and stuff like that, can I recommend this book called The Compass Chronicles, which is how to find your way around space in just 2 times. This is a study of different things that happen in the sky throughout the year from September back to September again, all reproduced from articles that were published in and I wrote this book a couple of years ago, and it's on Amazon, and you can buy it, and that will answer your question. It won't actually answer your question, but it's fun to read anyway. But all right, anyway. But no, that's a very fair question. That is a totally fair question, and I have to be careful not to really try to answer it because then I'll never get back to the subject. But basically, yes, it's like predicting periods of harmonic oscillation. Okay. What was I? Oh, but now here's the weird thing. I mean, everything is weird, but here's a thing that's relevant to this class that I think is kind of weird and blows my mind every time I think about it. Like the equation looks, but thank you for asking. Oh, and I'm sorry, the other private chat thing, totally, Copernicus was awesome. No, yeah, this is not an interruption. Sorry, that's the platform. Oh, cool. Okay. So no, cool things are happening in the private chat, particularly about, and I'm just afraid that I'm gonna get myself all distracted. But yeah, no, I love Copernicus, and my wife recently did a business trip to Poland, and well, not that, I guess before COVID, and I didn't get the chance to join her, and I'm really jealous that she did because I've never been to Poland. Although I'm 3/4 Russian, whatever. But I love Copernicus, and there is something in private chat that I'm going to check out, but I'm not going to check it now. Yeah, no, and this is cool. And here's a really bad joke I'll just make just to relate. Like my grandfather was from, was it? I always forget. I'm sure someone will correct me in the class. Oh my God, what's it called? Not the Ukraine. Oh my God. It'll come to me in a minute. But my grandfather, one of my grandparents, was from a part. Oh my God, someone will tell me, I'm sure you'll know. But there are a bunch of places that frequently went back and forth over history between Russian domination and Polish domination. You know, they were sometimes considered Poland, sometimes considered Russia, depending on who was in charge at any given time. And there's an old joke, and maybe some of you know it in your families, depending on where you're from. Oh, well, yeah, the USSR, right. But I mean, but not all of there's a particular part that was sometimes, yes, I mean, a lot of the USSR went back and forth. That is true. And actually now I'm all dating myself. I mean, history changes even faster than I can even. All right, this is a really dumb joke. I'm just going to tell just for the sake of it. But like, they used to ask my grandfather, well, which did you prefer? I mean, did you like it better when it was Russian, or did you like it better when it was Polish, where you were the village that you were living in? Was it better when the village was Russian or when it was Polish? And my grandfather would say, oh, definitely it was better when it was Polish for sure. And they'd say, really? Why did you like the village better when it was Polish? And he would say, oh, because the winters in Russia are terrible. Okay, that's just a joke. Get it? Okay, anyway. And I hope that doesn't offend anybody. But anyway, that's what I want to say Oh yeah, like Lithuania. Yeah, and it's just like right. Although that's not. I don't even know what 10-10 means. I hope that means it's good. I hope it doesn't mean I offended 10 out of 10 people. But okay. What I want to say about gravity that really is almost a joke. It's so weird. Is here's the deal. Look at this equation for a second. Okay, the equation. I mean, we do have to unpack the equation, but it's not. Where'd it go? Right. What I'm trying to stress right now, oh, cool. Oh, okay, cool. All right, thank you. Whew. And that's being beamed in from a laundry room, ladies and gentlemen. All right, what I want to say about both these equations is, you don't necessarily have to memorize them, although you will accidentally without trying too hard. Just notice they both have like an r squared in the denominator, and they both have like the objects in the numerator. Like both equations are saying the bigger the object, whether it's a bigger mass or a bigger charge, like the bigger the force will be. And they're also both saying that the farther away the objects are, the smaller the force will be, like r's in the denominator, right? And then it's also saying that that effect of distance is even in a way more powerful or more dominating than even the effect of size, because that distance thing in the denominator is being squared, right? So in other words, if the sun and the earth were twice as far from each other as they are now, then they would pull on each other 1/4 as much. Like that's what that's trying to, right? Because it's squared. Okay, so what? So who cares? Well, think about this. We're saying that the sun pulls on the earth, or a proton pulls on an electron, with a number of newtons, right? Like this is a mathematical thing. We're making a prediction here. And like, again, the K is a number that is always the same number for all objects. And the G is a number. So like it's saying we could do a plug and chug exercise now to practice. In fact, okay, one of the questions on the final exam is just like a practice of plugging and chugging in this. And if we have time, we could, but I think you all do know how to plug and chug. But if I give you any two masses, like the earth mass and the sun mass, and I tell you how far apart they are, you plug in the numbers and it'll tell you what the gravitational force is that the sun is exerting on the earth. Okay, whatever. It's a plug and chug. You get a number. That's very exciting. But now think about this. You get that force that you get from plugging in the numbers, and the force that you get depended on not only how big the objects are, but depends on how far apart, how close they are, right? But then who cares? Well, F equals ma. Once you have that force, you now have the rate at which one object will accelerate toward the other. And the earth is accelerating towards the sun, right? It doesn't mean it's always moving towards the sun. Like it has a velocity component off to the side. So it's often moving in a circle, not just in a straight line. But the earth is like accelerating toward the sun all the time because it's being pulled by the sun. So think about this. Just think, if there's no other objects going on, just in the simple scenario of like the sun and the earth, let's say, right? Pick just like one random moment that you just take a snapshot of the sun and the earth. In fact, let me write this down. All right, yeah. So I'm on this page right here. If you just take a snapshot in your mind of some random moment when the sun is over here and the earth is over here, the sun has this mass and there's 93 million miles between the two, and the earth has this mass. So the sun like reaches out its force tentacles somehow through empty space and starts yanking on the earth, right? According to this. And the earth starts accelerating toward it, according to this. Now, again, maybe other things are going on too that pull the earth another way, but just take the simple case, or picture at the beginning of the universe or something, or picture way out in space where it's not the sun and the earth, it's like two other rocks that are more isolated, if that makes it easier to picture. But whatever it is, we're believing, and I haven't said the weird part yet. Here comes the weird part, I think. But we are saying that if we believe in this equation, we believe that the sun is at some moment pulling on the earth with a certain number of newtons, and then F net equals ma, the earth will accelerate in at a certain meters per second squared. Okay, well, that means now the earth is closer, like the sun pulls on the earth, and now the earth is slightly closer to the sun. Okay, and according to this equation now, since the r just changed, since the distance between the two of them is now slightly different, or maybe very different, now the force has to change, right? According to the equation, if you believe it. It means the sun is pulling on the earth with a certain amount of newtons that then yanks the earth in. Now the earth is in a different spot. Now apparently the sun adjusts its pull and pulls like a little bit stronger now, let's say, because the earth is a little bit closer. And you might say, okay, why is that? I mean, I believed in the first pull. Why shouldn't I believe in the second pull? But there's nothing between the sun and the earth. So if the earth moved in a little bit and now the sun, the force from the sun has now changed according to that new distance, how the hell does the sun know that the earth just moved? Or excuse my language, but put another way, if we believe that this thing is always happening all the time in every point in space, what we're saying is we believe that at every single moment, somehow the information of the earth's location, its address in the universe, where it is somehow accessed by the sun. If we're saying that the sun is pulling the earth with an amount of newtons that depends on the R between them, that means that the sun knows the R between them. Now, not knows like consciously, like I'm not trying to be any weirder than it is, but I don't mean consciously, but just mechanically, just informationally. What we're saying is every time the earth moves closer to the sun, somehow that information of the earth's whereabouts must travel to the sun somehow, like the new address, the change of address, so to speak, must be somehow beamed in, or any word you want to use is going to be a weird word. I'm not trying to make it weird, but somehow if F is dependent on R, then the sun must have the R information. And not only must it have it, but it must get it somewhat quickly. Because if every moment the earth is being pulled by the sun and being yanked in, if it gets yanked in, now there's a new address. That new address has to be sent to the sun. The sun has to know the new address and now yank with a force that adjusted to that new address. Like it now has to change its F according to that R. So now it pulls more, but then that A's the earth more. So now it happens again. In other words, and all in reverse too, if the earth is pulling on the sun or if the earth is pulling on the moon. In other words, any minute that you believe in F equals GMM over R squared, that actually means you have to be believing that each object involved has access to the R information. Every time the earth changes its location relative to the sun, somehow the sun must find that out and pull more strongly or more weakly accordingly. And again, I'm not saying consciously, I'm not trying to make it any weirder than it is, but even unconsciously or inanimmately, that's very weird. Let me be even more specific. Let's talk like quantitatively. Let's even say that you can picture that somehow. And at some level I can, but at some level I cannot. Let's say that you're believing me. And by the way, I'm not lying to you. I'm saying these equations, we believe in them in physics, and we believe in them primarily because they work. But that doesn't mean that they make sense. I mean, that doesn't, and it doesn't mean we would have believed in them until we saw that they were working. Like we didn't come up with these from logic and say, well, logic would dictate that there would have to be these equations. Heck no. Like they actually fly in the face of logic if you think about it a certain way. We are specifically saying, so if I can be more specific for one more minute, if we believe F equals GMM over R squared, or correspondingly, if we believe F equals KQQ over R squared, and I am saying that, I'm saying anything we believe about suns and earth and planets or planets and moons, it turns out we also believe about protons and electrons, or I mean, at least in this context. And, the problem with protons and electrons is I could tell you anything and you'll either totally not believe me or you'll totally believe me either way, because we can't see protons and electrons, right? And we're just all used to accepting these things in science, being like, oh yes, the electron orbitals and P and D, right? And so either you believe it all or you just have gotten used to just accepting things without actually caring about believing them. So that's why I'm trying to relate it back to gravity, where you can at least picture it and you could at least ask yourself whether you really want to believe it or not. What we're literally saying here is that as the sun pulls on the earth and the earth comes in toward the sun, we're saying that every new place that the earth occupies, somehow the information of that new place must be getting to the sun in time for it to adjust and make a new pull for the very next step. So what I'm really saying then is, Okay, first and foremost, what I'm saying is if you believe in action at a distance at all, like what, I mean, once we say there's any kind of action at a distance, GMM over R squared, KQQ over R squared, if we say the sun pulls on the earth through empty space, we are necessary, and especially if we say that we can quantitatively predict the number of newtons, and especially if we say there's a mathematical relation between the number of newtons of the pull depending on the actual distance between the two objects, then we are literally saying that information describing one point in space must somehow be able to get to some other point in space, right? Like we're saying that what's happening over here in space has access to the quantitative description of what's going on over here in space, right? Whether it's the sun having access to the Earth's size and its location, or it's a proton having access to an electron's size, charge, magnitude, and its location, we're saying that somehow the information of over here must be able to get to, travel to, transmit to, I don't know what, over there. And like, that's already weird, I think, but to be super specific, then to break it down, oh. Okay, now I'm going to say something like already what I'm saying, I'm not saying that anything is true or false. I'm saying what we believe in physics, right? And I'm saying we have these equations in physics, GMM over R squared, KQ. I mean, I am saying they're true in physics, right? But I'm not saying that they're logical or not. I'm just saying that they are claims in physics and they do seem to be supported by a whole bunch of data. But now I want to be logical for a second. What do I mean by logic? I mean, the heart of logic is, at the heart of logic is what's known as Aristotle's law of the excluded middle. The heart of logic is that for any statement you can ever conceive of, call it P, P is either true or it is not true, right? Like this is what all of logic flows from that assumption. That doesn't mean all of life flows from that assumption. It doesn't mean that all of what is common sense or reasonable flows from that assumption. It means that all of what we call logic flows from that assumption. Like this is anything we ever do that's mathematically strict or scientifically strict comes from this idea that we do not contradict ourselves, right? Now, again, like in emotions, that could be different. Like I can love you and not love you at the same time, I suppose, emotionally. But like in math, right, something is 2 + 2 either does equal 4 or it doesn't, right? But it doesn't both. But in logic, you can't, something is not true and not true at the same time. And something either is true or it is not true. There's no middle ground in at least Western logic upon which or from which we derive all Western mathematics and Western physics and all that, right? So just on that, if you just for a minute imagine that somehow we're believing that the information of the Earth's whereabouts somehow have to get to the sun in order for the sun to know exactly how hard to pull on the Earth, which is what this equation seems to suggest, right? And it's not suggesting how that happens or that it should happen. It's just suggesting that evidently that does happen. Well, logically, that process would either have to take time or not take time. What I mean to say is, if you even just imagine for a moment that the sun somehow has, or even not even the sun, but like the place where the sun is in the universe, that somehow the information of where the Earth is, like, gets sent to that location, right? And again, I'm saying that would have to be necessary for the number of newtons of, let me say it again, the sun pulls on the Earth with a certain amount that's based literally on where the Earth is. So it pulls on the Earth, and then the Earth is now a little bit closer. Now, evidently, the sun pulls on the Earth with a different amount based on this new data of where the Earth newly, freshly now is located. Evidently, that new data of the Earth's new location evidently somehow has gotten to the sun, and the sun is now pulling harder or less hard if the Earth is farther away, right? And so we're believing, at least for the moment, according to this equation, that somehow the information of the Earth's whereabouts gets sent somehow to the sun. Well, just to really investigate how weird of an idea that is, if it already doesn't sound weird enough, like what I'm saying is, let's now investigate the only two logical possibilities that I could conceive of is that process of the information going from the Earth to the sun. Well, either it takes time or it doesn't take time. Like, there's no other possibility, right? Either literally the Earth has moved and now the Earth is in a new spot. So now somehow it sends a signal to the sun that travels maybe very, very quickly. But like, possibility number one is it travels very quickly, but at some kind of finite speed, maybe very high, but still finite. In other words, possibility one is it takes some amount of time for this adjustment to occur, for the update to reach the sun. That's possibility number one. Possibility number two is no, that doesn't happen. The information just gets there immediately. Now, again, literally, there's no other possibility, right? I mean, if this is happening at all, this is what I mean by pure logic. I'm not saying that either this process has to be red or green, like, because then you could say, well, there's other possibilities. Couldn't it be purple? I'm not saying that. I'm saying either this process has to be red or not red. I mean, I'm just using red as an arbitrary example, right? Like, this process either has to be tall or not tall. I'm not saying, like, right? I'm just saying it either is or it isn't. So if this process is happening at all, if the information of the Earth's whereabouts are somehow arriving at the sun, and by the way, again, you might say, well, they're not. That can't even be. That's insane. Right, maybe so, but then these equations don't make any sense. And this whole idea of action at a, like, the minute we believe that something can pull on something else through empty space, we're automatically in this jam, is what I'm saying. So I'm really trying to emphasize here, what I'm really trying to delineate is in as specific way as I can, is action at a distance is weird, right? The minute we believe that something can pull on something else through empty space and in a manner that depends on how much empty space there is between them, which is totally what we're saying in both of these action at a distance equations. If the suns pull on the Earth, or if a proton's pull on an electron, depends on how much space there is between them, then that means the moment that pull is enacted, and the moment that the space between them changes, somehow the new space amount has to be sent somewhere. I mean, it has to get to each of these objects. And so then if you believe that, then I'm saying, well, then logically, either the transmission of that update takes time or it doesn't. It either travels at a finite speed or it travels at an infinite speed. Those are the only two possibilities. And why am I taking so long to say that there's only those two possibilities? Because if you think either of those possibilities doesn't make any sense, I would say you're right. And if you say both of them don't make any sense, I would say you're right. Like, something is very crazy about either of those possibilities. Why? Well, let's look at the first one. If it takes time for this update to get from the Earth to the sun, well, that's crazy, because that means every moment the Earth moves, there's a delay. Like, now the new information has to get to the sun before it can even pull anymore. So it waits, and it could be a very short amount of time, right? But if it's any amount of time at all, then there's a delay, like a, what do you call it? Like a latency thing, like on the internet, right? Like, but we're now saying in real life, in nature, there would be a delay while the new information, the new update of the new address is being sent from the Earth to the sun. So there's like a freeze, like where nothing new can happen, where there's no new pull. I don't know if the old pull is still in effect while we're waiting for the new pull, or all pulls are suspended, but there's some sort of delay until the information arrives there. And then the information arrives there, and now there's a new pull. But of course, then the new pull will result in a new location. So then there'd be another delay. In other words, if you believe the first possibility, then that means all of what looks like a smooth movie in nature is really a strobe light effect all the time, right? It would say that all of what's happening in nature is actually staggered and like with all of these delays between every single moment. Like there would have to be time between the times. That's crazy. That doesn't make any sense. But on the other hand, if that's not happening, if there is no, so in other words, a delay. So possibility one is delay, but a delay between every single thing that happens in like in the universe. So perpetual delays, like in other words, perpetual strobe light effect. That's crazy. But the other possibility is that that's not happening. And that the other possibility is let me write that clearer. So possibility one would mean delays like all the time. Latency, you might, like what happens with, internet signals. But the other possibility is that that's not happening and that the information is getting there instantaneously without a delay. But then that means that the information is getting there instantaneously. That means that the information of the Earth's whereabouts is somehow getting to the sun in no time whatsoever. In other words, infinite speed. But if that information can travel, if information of what's going on over here in space can travel to over there in space at an infinite speed, well, that means it gets there in no time, regardless of the distance, right? If it's infinite speed, it doesn't matter. Then that means it's like any numerator you want over zero, right? I mean, like the speed is any distance you want over the same time of zero. And that means it doesn't matter how far away you are at all. The information will always just get there at instant speed. So that means that if that's true, that means that the universe is perpetually in communication with in instant. That means that all distances don't matter, right? That means that whether the Earth is like 5 miles from the sun or 50 million parsecs from the sun, it can communicate with the sun just as easily either way. So that means that the Earth is simultaneously all the time communicating with all parts of the universe at all times and in no time. In other words, then distance doesn't mean anything. That's crazy too. They're both crazy. They're both right. I'm not trying to convince you they're wrong. Evidently, the equation is right. But there is something very disturbing about the notion of action at a distance. So disturbing that now I'm just babbling, but so disturbing that let me turn your attention to that quote that I put in the internet, in your stream last time. And let me see if I can pull it up as well. But this quote that I put in, okay, is a quote. Oh, good. I'm sorry. I mean, thank you. And I'm right. I mean, it should, right? I mean, look, and I hope she's just sort of kidding, but I hope she's sort of like not. I mean, I am trying to, I'm not really trying to hurt anybody's head, but I am definitely trying to say, like, yes, if you think about physics in a certain way enough, it can sort of drive you crazy for sure. But if you accept these things without thinking about them, you're crazy. Like, I mean, that's what's cool about, like, the universe does not make sense. I mean, I think it makes more sense than I'm making it sound like I think it does. Like, what I love about thinking about these things is every time I think about them, I do actually get more and more of a glimpse in the sense of the universe. But the sense is not what I thought it was when I first started looking at this. I can assure you all. And I think that's true for, for anybody who likes this. Like, it's weird. What's really weird is every time it works out as less weird than I thought, but then it gets weird. Well, what I mean is this, I'll show you. Let me pull up that quote. So that quote that I put in your stream that hopefully maybe, oh, sorry. Yeah, no, right. Me too. I mean, the great thing, yeah, it gets complicated. Yeah. The thing is too on what, sorry, on what And I do want to pull up this quote, but I'm psyched. I mean, and we should take a breath, obviously. But notice, by the way, if you, and also I know you're being polite, some of you, and I appreciate that. Like, but you notice if this is at all complicated to you, if this sounds at all weird or at all interesting, notice it's this weird. We're not even doing math, right? I mean, I'm pointing to a math equation, but it's not the math that's making this hard, right? It's like just the basic assumption. The math is actually the relaxing relief. That's what people don't realize when they first go into science or physics. They think it's the math that's going to be the intimidating thing. But you get to a certain point in science or in physics where you're just craving the math because the math looks like it makes sense compared to all of this. And at least once the math is set up, then you know what to do and follow procedures. It ain't the math that's making this hard. The math is what makes this easy in a way. I mean, math too can get crazy. But like, if we're having a headache at all here, it ain't because we don't know how to take a derivative or something. It's because like I mean, it's just like, so let me put another, all right. Oh, cool. Yeah, no, good. I'm glad. No, me too. And look, when I love math now, and I'm fair, you know, I like to think I know a lot more math than the average person on the street for sure. And I actually know a lot more math than most people in the science department, I guess, because what they do is less mathematics. Most, not all, not Petrarco, for example. But I'm pretty proud of where I've gotten in with my math, and I love math, and it gets pretty sophisticated. But I'll tell you, when I first went into all this, it wasn't because of the math. I mean, I love math now, but it was the conceptual stuff that hooked me first, and then I was sort of forced to learn the math to keep up with the concepts. But cool, okay, right. And if you, right, okay, and so what the heck am I trying to say? No, but good. I'm glad you guys. I think I love the attitude that all of you have towards this, and wait, I'm losing my thread. I want to show you this quote. Oh no. One thing I just do want to say about like what all of you are saying in the chat, particularly like the words of Rahela and Quasi, like just one thing to note. Yeah, all this can get very complicated and very complex, but do note one thing. In fact, I want to say this if I've never said this before, this is like, just remember, the opposite of complex is not easy. And the opposite of simple is not hard. People confuse the two. I'm not, you guys are not. I'm not saying you guys are confusing anything, but it's very easy to fall into this act that we know that simple and complex are opposites. And we know that easy and hard are complex. Are opposites. People end up often thinking that the more complex something is, the more hard it is, or they think the opposite of complex is easy or vice versa. That's all ass backwards. That's not right. Like if you really think about it, what it means to analyze or understand or think about, like, and I used to use this example. I don't know if I've used this example in your class. I'll just say very quickly, like when I used to begin physics in other classes, if analyze is to break apart, right? I mean, literally, you know, from chemistry, analyze is to break apart, whether it's in reality or in your head. And to understand things usually means to break them apart. So complex things actually we can understand by breaking them apart. So for example, and again, I'm not asking right now, I'm just saying, maybe I did this in this class, but like I think I did in this class, well, actually, but I used to all the time on the first day before anybody knew anything or knew what to expect with me or anything, I used to ask, what's a unicorn? And people tend to be able to break down what a unicorn is. And they'll say like, it's a horse with a horn on top of its head. A unicorn is sort of complex. It's like complex means many parts. And analyze means to break something down into its parts. So you can analyze a unicorn and say, oh, it's a horse with a horn on top of its head because you've broken it down into its parts. But then if we ask, what's a horn? That's a much harder question, right? Because a horn is simple. A unicorn is complex. It has many parts. Right. Well, one thing yes, definitely there's like translation things that go on. And like, honestly, secretly, what Walters and I think we're really supposed to be doing here is we're supposed to be translating. Like, what this course is really about is about translating stuff. And first maybe into English and then maybe into math or whatever. But right, physics is more like learning a language or a skill than it is learning a topic of not, you know, a bunch of pieces of knowledge. but if you ever think about it, it's easier to break down to understand complex things is easy. You break them down into their parts. A unicorn equals horse with horn on top of its head. But now try to understand what a horn is. That's a lot harder because there's much less to break down. What are you going to break it into? Just like understanding things moving through space and time is one thing. Understanding space, understanding time, that's much harder. Where are you going to go with it? Like, we all know what space is, kind of. We all know what time is, kind of. But really understanding them, what are you supposed to do? How do you break down space? How do you break down time? That's actually why physics is hard, is because it's not complex. Physics is simple. That's what makes it not easy. There's not as much room to break things down. But anyway, and you know, all these questions, the universe, and is it like the hard thing is the simplicity, not the complexity. But anyway, this quote that I put in the chat, not in the chat, in the Google Classroom, let me pull up for a second. This quote, this is an excerpt from a letter to Sir Richard Bentley. Sir Richard Bentley was a contemporary of Newton's. He was actually like a hero of, we don't hear about him much these days, but you know, even our heroes had heroes, right? I mean, even our great teachers had teachers and authorities that they turned to in times of crisis and stuff like that. And Sir Richard Bentley was like a Don at Oxford or at Cambridge, a major educator and a major figure. And lots of people would come to him for advice and counsel about whatever was going on in the philosophical, the scientific, the academic community at the time. And at the time, someone wrote a letter to Sir Richard Bentley, someone who had heard about the Newton's blossoming theory regarding gravitation. I mean, it was very new and very fresh and hadn't like been released to the presses yet and whatnot. And someone wrote to Bentley with a critique or a concern or an objection to what they understood to be Newton's young gravitational model, the model that we're talking about right now, this notion of action at a distance in GMM over R squared. And let me just pull it up for a second. Hold on. Where did it go? Letter to Bentley. Hold on one second. I mean, I know you have it. I just want to get it up so you can see, or at least I can see what I'm talking about. Sorry. I'm losing all my momentum here, of course. What else is new? Well, okay, hold on. I'll actually go to. Hang on. Sorry. This is a total killjoy, total party foul here. But I know it's here somewhere. Or did I put it in? I could have sworn I put it in your. Oh yeah. Okay. Here it is. Okay. All right. So yeah, put in the classroom. It's called Letter to Bentley. So now I'm going to pull it up on the screen share. Oh yeah. Okay. No, thank you. I'm glad you got. I think I got it now. But thank you, Riley. That's awesome. And it also means you're paying attention. Thank you. I totally appreciate it. Okay. But here we go. Right. Okay. This is it. Right. Someone just came. Okay. Open. Oh, I see what's happening. Sorry, 1 second. So graceless. Oh, I see. Why do I care? I don't know why I care. You should come. Right. All right. I don't know why that improved anything. It didn't, but okay. So everybody's looking at this again. Hopefully you have it in your own stream, and I appreciate that Rahel at least does. Now I'm going to read this out. All right. Now remember, so what this is, I know you haven't heard of Richard Bentley, but like, take my word for it. He was like a big dude. This is an excerpt from a letter that someone wrote to Bentley And this is about Newton's theory of gravitation, about the action at a distance idea, okay? And we're going to talk about who wrote the letter in a second, but let's first look at the letter itself. I mean, this excerpt from the letter. So, as it says at the top, regarding Newton's law of universal gravitation, and regarding the premise that some kind of force could be exerted without any touch. So here's a critic writing to Bentley, and he says, it is inconceivable, right? And, I don't know if you've seen Princess Bride, but like inconceivable, like you can't even think about it. It is inconceivable that inanimate, brute matter should, without the mediation of something else which is not matter, operate on and affect other matter without mutual contact. Let me go on. That gravity should be innate, inherent, and essential to matter so that one body may act upon another through a distance, at a distance through a vacuum. These are real words, right? These are not my words. These are, and in fact, they really are the real words. By the way, this is not even a translation because this was written in English. Sort of 17th century English, but so that gravity should be innate, inherent, and essential to matter so that one body may act upon another at a distance through a vacuum without the mediation of anything else by and through which their action may be conveyed from one to the other. And here's the key, the last line, please look at it, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Now, and so this letter was written in 1693. Newton lived from 1642 to 1727. Let me just emphasize that again in case you're missing it. This is very, maybe it's old style English, but it is very strong and very direct, I think. Like, he's not messing around. This person is saying, if you just look at the bold parts, like the big parts, that gravity should be innate, inherent, and innate and inherent means like in and of itself, like true necessarily. In other words, this idea I was saying before, that if we say that gravity is innate, inherent, and essential to matter, we're saying that matter automatically exerts gravity without having to try or do anything or like touch anything or move in any certain way. It just like happens. Like that's what we mean by innate, inherent, and essential to matter. And by the way, according to Newton, we would mean all matter. Like that is the theory of gravitation here, that all mass points, all thingy things just automatically do this. And by the way, again, if we now go to the 18th century, the late 18th century, early 19th century, then Coulomb, like Newton is saying this about all masses. They don't even know about atomic theory or anything like that at the time. Then we get to Coulomb. Now we're believing in protons and electrons, which we believe all matter is made up of. And Coulomb is saying that all protons and all electrons automatically do this, just pull on each other through empty space, right? So this dude, this critic who's writing about Newton and writing to Sir Richard Bentley, he's literally saying that gravity should be in it. And remember, Newton's like I didn't call him a genius then, but like Newton is no slouch. He's not like just some dumbass. He's Newton. Not that he was Newton then as such, but he kind of was. So this guy is saying that gravity should be innate, inherent, and essential to matter is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. That is literally saying, I think you understand. I know you understand. But he's saying is to me so great. When he says no man who has in philosophical matters a competent faculty, okay, competent faculty does not mean a skilled teaching staff, right? He doesn't mean, like, I have a competent faculty between Walters and Wu and Liu. That's not what he means here, right? He means faculty, like facility, like ability, like capacity. So when he says who has in philosophical matters a competent faculty of thinking, he's just saying anybody who is like at all remotely thoughtful, who is not an idiot, right? So he's saying is to me so great an absurdity that no man, and like he should also say or woman, but he didn't because he wasn't that way. But he's saying that it is to me so great an absurdity that I believe no person who can think at all could ever believe this. Right? That's what this person who's writing to Sir Richard Bentley is saying about the Newtonian theory that we're totally trying to teach you here. Like it's standard physics issue here, the GMM over R squared and the KQQ over R squared, which we do want you to learn from the final exam, but I want you to learn it in this context, that it is, at least at the time, it was such a controversial idea that this guy is writing to another expert and saying, dude, this isn't just like flawed. This isn't just like he didn't carry the two. He's saying, this is idiotic. How could you possibly believe that one object could affect another object without touching it at all? And he's, I mean, and what are his reasons for thinking that? Well, they basically are the ones that I've been taking like the last 20 minutes to try to outline to you. I mean, he doesn't get, we're not going to get into the whole rest of the letter, or he's not going to get into the whole rest of the letter. But the reason he thinks it's absurd that something could affect something else without touching it is that basically what I was saying before, then that would mean that it knows where the other thing is, even though it's really far away, and it would know where the other thing gets to, even when the other thing moves, which means somehow things have to be, in other words, to pull something else without touching it. Oh, okay, actually okay, I'm going to switch the screens now. We're not done with this quote, but I just realized that maybe for the first time why I think this is so weird. Hold on. What I'm trying to say ultimately, that I think this letter is trying to say, is, I mean, why it's weird to think about something pulling something else through empty space is that if you believe in things pulling on each other through empty space, you have to at some level believe in information being sent through empty space, information about one address in space somehow being transmittable to or accessible by other locations in space. And that, I'm not saying that's impossible, but I'm saying that is a headache of an idea, because the minute you believe in information being transmitted from one point in space to another, like all the time, under all circumstances, then you have to at least wrestle with the question of how, you have to start asking the question, how the heck does this information get from here to there? And the first question one might ask about how does it get from here to there is, how long does it take? Does it take any time or not? Geez. Okay, now, here's the thing. I'm not just ranting and raving. I want to pause for a second and say that letter that was written to Richard Bentley, that letter that was written about Newton's theory, okay, was written in the, well, it says on the bottom, it was written in 1697 or whatever, like in the late 17th century. It was a critique of Newton's work. So it's about Newton's work. It was sent to a guy you never heard of, I maybe never heard of, named Bentley. And to be honest, I don't know much about him other than this either. Like, he doesn't come up a lot, but he did come up a lot back then. So it was written about Newton to a guy that we don't talk about very much, but it was written by someone that you do know something about. You might notice that on this is one of the reasons I took the pains to put it in your stream. And it's not like you can be tested on it or something like that. But one of the reasons I want you to have this document sort of clearly footnoted and stuff is I want you to know it's written about Newton. I want you to know the exact words. I want you to have access to the exact words. I want you to know that it was written to Bentley, but you might notice that I didn't write on the sheet who wrote it. I want to take a couple minutes for us to, and I know you're all in front of the web right now, like try to resist the temptation. I mean, I can't enforce it, but without Googling or going crazy, just for a moment, let's just see if we can figure this out. I'm going to tell you that you actually have heard of the guy that wrote this criticism of Newton, the guy that had the guts to say that Newton wasn't only possibly just sort of kind of maybe a little bit wrong, but absurdly wrong. You've heard of, I believe. Oh, okay. Now, I just got one guess in the direct chat. Very good guess. I'm not going to say names if it's in the direct chat, but I want to address, and I do, because I do want to hear guesses from all of you. And it's fine if you do it public or private. One guess that I just got in the private chat is a very reasonable guess, and I do get this guess a lot. And it also reflects that someone did not just go Googling it, and I appreciate that. So someone just guessed Einstein. Totally reasonable guess for 1,000 reasons, because many of us may have heard that Einstein did ultimately advance our understanding of physics so much so that he did in some ways topple some of the knock down some of the ideas of Newton. That is a historically reasonable thing. I mean, that's like a smart guess to say Einstein, but it's not right. Okay, and Hawking, which I also just got in the direct chat, is another good guess, and Hawking is like Einstein. Here's the thing, though, that I want to, and these are good guesses, and I want more guesses like this. And I appreciate, again, that we're like not cheating. I think it's worth not cheating on this for a moment. Einstein and Hawking are very good guesses. They show that someone's thinking reasonably. Here's the thing, though. The letter was written at the time of Newton. I mean, it says at the bottom, like the letter was written in the late 1600s, 1690. 1693. It was Sir Richard Bentley lived at the time of Newton. So this letter was written right when the Newton thing was just happening. It's like a very early critique. And Einstein actually did his work like in 1905 and 1925. Like Einstein is like a 20th century figure. And then Hawking is like a 20th and 21st century figure. So totally reasonable guesses, except I'm going to tell you all right now, no, this critique was advanced by a person that you have heard of, but it's a person from long ago, from the 17th century. That makes it harder to guess, but it is guessable. I mean, let me just look in the chat if I'm missing anything else. And it is worth. I think you're gonna find this worth that other people have when we've done this in class before. Like if you can resist the temptation to try to cheat. Hawking and Einstein are reasonable guesses, but I'm telling you all now, it's someone actually. Okay, and now Coulomb is an even better guess. Someone in the private chat just guessed Coulomb. Coulomb makes this even more, it's actually a really, really smart guess, especially given what we're talking about. But even Coulomb, you might not know. I mean, how could you know Coulomb even? Yes, no, I know. It's taking a lot of self-discipline for you guys to resist Googling this right now. And maybe I don't know how long you can hold on. Now I'm getting a lot of guesses in the chat. So Coulomb happens to be a little bit later. Coulomb is like late 18th century, early 19th century. Not that you could have known that, but I'm just saying it's true. Now, Galileo is a great guess. Someone just guessed Galileo in the private chat. The thing is, Galileo is a little good guess, very good guess. Happens, I'm just saying, it happens that Galileo is before Newton. In fact, weird coincidence, I might have mentioned, or maybe I never mentioned this class. As a matter of fact, Galileo dies in 1642. And then on Christmas of 1642, Newton was born. And a lot of people make like all kind of mystical connection about that. And then something else, there's some other connection to Einstein and Hawking that comes later. But the fact of the matter is Galileo is dead by the time Newton is born. I mean, people like to think that like the soul of one passed into the other, but that's up to you guys to, but so Galileo's a great guess, but Galileo's a little bit too early. Coulomb's a little bit too late. And I'm not saying you could know this. I think you'll find this worth it if you can keep resisting the temptation. Oh, wait, I'm looking in the chat still. All right. Yeah. So these are good guesses. And I'm telling you, and you will know when I tell you, or when somebody guesses the answer, you're not going to say, oh, I never heard of that person. You will have heard of the person. It doesn't make it easy. I'm not saying it's easy. And I'm not, and Usually the only people that ever do get this right do cheat by going on the web. So it's not, you shouldn't feel silly if you don't get this right, but you're going to find it interesting once you hear the answer, if we do figure it. Okay, right. And we are grasping at straws. Now, someone just, you know what? Someone just guessed Da Vinci in the direct. That's an amazing guess, because that time, and Copernicus is a great guess too. We are in the right time frame now if you're guessing those guys. Those are, I mean, maybe they're a little bit early, but those are definitely the right time frame, but it's not right. And I'm going to, and I'm telling you, I'm not doing this to make you guys feel stupid. I promise. Not quite the reverse. I'm doing this to make a point. Like if you think your head already hurt before, this is partly so that your head will hurt when you hear the answer. It is not to make you feel silly. And believe me, I would never have guessed the answer if I didn't just happen to know it. I mean, but that doesn't mean it isn't guessable. And it doesn't mean you won't know the answer when you hear it. It's one of those weird things. All right. Do you want me to? Okay. I'll tell you what, I'll make you a deal. If I've heard a lot in the direct chat, which is cool. And I totally understand why no one's going public with this. I do understand. But I'll tell you what, if I, okay. Yeah. You can have another minute. Great. Yes, absolutely. And it will be worth it. I promise. I mean, yeah. So I'll give you another minute because someone, yeah. Okay, cool. All right, so I will pause for a second. So I'm also gathering, by the way, it sounds like, because so many people are participating now in the private chat and the public chat, I'm gathering that you totally do get what I'm saying. I mean, it seems like we all are with me. Like you get what's weird about action at a distance. You get that this person is criticizing it. Right, and you get that. I mean, I think you get it, right? Okay, and you get that action at a distance. So Yeah. Okay, cool. Thank you. Okay. Yeah, it does seem like you totally are. What time is it? 6:40. Okay. All right. So I'll pause for a second. In fact, should I use the bath? I kind of want to use it. Yeah, I'll pause for a second. You can even talk. I'm gonna run to the restroom for a second. Oh, great. Oh, okay. So I'm back. A couple of good questions in the. So it's Hawking would be a good guess, but Hawking might have said something similar, but he's a little too modern, so it's not actually Hawking. But then there's a question in the direct chat: is it an Enlightenment philosopher? That's a great question. That shows that you've been going to college. Is it an Enlightenment philosopher? I would not call this, I mean, that gets into maybe interpretation. I would not call this person an enlightened philosopher, but I don't think you would categorize the person that it actually is as an enlightenment philosopher, but that is a very fair question. I want to say no, but I'm afraid you might get mad when you hear the answer. You might say, oh, yes, he was. You might be, I might be out of my league on that, but I don't think. Oh, Bohr is a good one too. That's a little bit later, but you couldn't necessarily know that. Well, it's quite a bit later actually, but you wouldn't necessarily know that. It's not Bohr, but Bohr is a good guess. Should I give you a hint? Now I have to say, I mean, a guess that I just got in the direct chat, it's a really good guess. It might be the most, so a guess that I just got was Hooke, as in Hooke's, I mean, someone just guessed Hooke, as in Hooke's law, as in the Hooke's law for a spring, like that we spent so much time in this course. Now that's a great guess for a number. I mean, they're all great guesses, but that's particularly interesting guess for a couple of reasons. One, Hooke is so relevant to this course. So like it would be fair for me to know, for me to think that you know who Hooke is. Two, Hooke absolutely is I mean, it's not right. It's okay. Sorry. It's not actually right, but I do want to dwell on it for a second. Hooke is a fantastic guess because Hooke was a contemporary of Newton's. Like he did live at the same time as Newton and Bentley, and was a major rival of Newton's. Like he and Newton did not get along. They disagreed over some very fundamental things, including like the ultimate issue of this class. I'm getting it twice. Okay, so two people, Sam Clark. Wow, that's a very educated guess too. Very educated. Also not right. But let me just say one more thing about the Hooke that I like. Hooke was a rival of Newton, and they disagreed. Among other things, they disagreed about whether light is a thingy thing or an unthingy thing, which is kind of the ultimate thing of this course. So, and they really did live at the same time. So that would be, and I think Hooke even was British, I think. So that would be, but it's not Hooke, but that is a very reasonable guess. I mean, if I made this up myself, I'd probably make it up so that it was Hooke to make the course perfect. Oh, that's a great question too. As far as, so someone put in Sam Clark, which is a great guess, also a very educated guess and almost above my pay grade, but it's not actually Sam Clark. And then someone put in the direct chat as like a hint thing, is the person that we're thinking of, is the person English? Fair question to ask as like a hint or 20 questions. And yes, the person that I'm thinking of here is actually English or British or whatever you want to, but then also someone put in the direct chat, and it's great because it'll move me along too. Someone just put in the direct chat, and I'm only saying someone because you guys are putting direct, so I don't want to mention your names, but you all do deserve credit for saying these things. Someone put in the direct chat, who's right, Hooke or Newton? And I assume they're referring to the fact that I just said Hooke and Newton disagreed over whether light was a thingy thing or an unthingy thing. Well, that is a fantastic question. And in some way, the answer to that is read this book where we explore. But no, as far as this class is concerned, Hooke is right. I mean, I haven't said that yet, but one of the punchlines of this class is, in the end of the day, in this class, we will say that light is a wave. Now, the truth is a little bit more complicated than that, honestly. And for that, please take Physics 103 with me or whatever, do research with me. But as far as the final exam of this class is concerned, we're ultimately going to land on saying that light is an unthingy thing, that it's a wave. And I will get back to that in 5 minutes and for next time. But as long as someone's asking to keep me on track here, we're ultimately going to say in this class that light is an unthingy thing. And therefore, that when light comes from stars to us, when we see that the star light that we receive is lower frequency than so please, I know I'm like a little bit to the side here, but it's such a great question. And I know you're all paying so much attention. We're ultimately going to say in this class that light is an unthingy thing, i.e. that light travels as a wave. I have to show you why we think that. So I still have, thank God, 2 more hours next week. But if I can get you to at least believe that light is a wave, then you'll see, then if you accept that premise, then it will make sense to you with all the time that we spent on the Doppler effect. And I know I've said this before, I'm going to say it again now because I want you to know this coming out of the course. If you can believe that light travels as a wave, and if you can believe that frequency of light waves is like frequency of sound waves, and I'm not forgetting where we are right here. I'm looking at the time, but I'm just so pleased that someone just asked that. Remember, frequency of sound waves is translated by the human brain as pitch, right? So when a Doppler effect happens for sound, like if something's moving toward us and it sends out a certain pitch, like a middle A, but if it's moving toward us, we'll hear that pitch is slightly higher. Like they'll send 440, we'll hear something like 490, whatever, like A sharp, because the thing was moving toward us. And if it was moving away, we would hear a flatter or lower pitch, right? Like in that, we've been practicing with Doppler effect. Well, if light is a wave, then a similar thing happens. Frequency for light is translated by the human brain as color, right? I mean, if light travels as a wave, then the frequency of light waves are translated by us as colors. So when starlight is sent to us, we receive starlight at a certain frequency, a certain color. It turns out, I'm telling you, when we measure the frequency of light that we receive from stars, we tend to find that the frequency of that light as we receive it is in general lower frequency than the frequency with which it was sent by the star. And we know what those frequencies are. We know what frequencies the starlight is sent at because we know the chemical composition of stars when we do spectroscopy, as you learn in other classes. So I know this is a bit of a digression, but it's not, because it's like the punchline of the whole course. I'm just telling all of you guys that if you're willing to believe for any reasons that Joe gives you on Wednesday or I give you on Monday, if you're willing, and I'll look back at the chat in one more second, but this is just like too important not to say. If you're willing to picture light as moving as waves, and you're willing to see how the frequency of those waves get translated as color, just like frequency of sound waves is pitch, frequency of light waves is color. Well, starlight in general, when we measure its frequencies, we tend to find that the frequency of starlight as measured on Earth is lower frequency than the frequency of that same light as would be measured by the star, according to spectroscopy. We get light from stars, in other words, the light that we get from stars tends to be always shifted towards the red end of the spectrum. It's lower frequency. It's Doppler shifted toward lower frequencies, i.e. more reds than violets. The light that we get from stars is more red according to our measurements than it is according to star measurements. And from that, we infer that stars must be moving away from us. We believe that stars in general are all moving out and away from wherever we are always, because the light we get, the light waves we get, demonstrates Doppler shifts toward lower frequencies. Lower frequencies mean source moving away. This is why we're obsessing so much about the Doppler effect with you guys, like with the sound and everything. If you understand the Doppler effect for sound, then we're just asking you then extrapolate that or extend that analysis to light, if you can imagine light being a wave, and you'll see why. And if you've ever read about this, the red shift, the so-called red shift in outer space, means the Doppler effect of starlight. And it is the effect that we see light as redder than it was sent. And therefore we infer that stars in general are moving away from us at speeds that we can calculate based on those shifts. And from that, we get something called Hubble's law, and particularly we get an expanding universe model. We believe in the expanding universe because we believe in the Doppler effect as it applies to light. So, and we believe light is a wave, just to answer the one question in the chat. And I even do want to get back to that, but I know it's 6:50. Okay, and now, oh yeah, physics, philosophy. Oh, okay, so now I'm going to, by the way, yeah, yes, physics, philosophy, I mean, they're both near each other in the alphabet for a reason. No, and in fact, physicists weren't called physicists until recently. They were called natural philosophers until, but anyway, let me go back to the chat. Okay. Yeah, we're driving ourselves crazy. Okay. Oh, Descartes is a very good guess, actually. Descartes, he's a little bit earlier, but that's a very good guess. Boyle is a little bit later, also a good guess. Okay, Robert Smith. Boy, you guys are educated. And Barclay, I'm impressed that you guys know about those. I didn't know you knew about those guys. And some of them I know about more than others, but Barclay, Smith, those are very educated guys. Like, you're getting your tuition worth. I'm impressed, but they're not right. I will. All right. So because it's 6:50 and because you clearly are paying attention and I love it and you're totally involved with me, I will end the madness. Wait, wow, Robeson. Guys, you all deserve a lot of points for this. All right. I'm going to end the madness and tell you, and I'm going to bring this full circle to tell you what this all has to do with the expanding universe and all that. Are you ready? Can I tell you? Or, I mean, oh, Hume. I love Hume. God, I love him. He's a little bit later too, but God, I love Hume. But it's not Hume. Can I tell you? I mean, can I get permission from someone to tell you? Okay. Awesome. Okay. And you might get really pissed off when you hear this, but it's not a trick and it's not a joke. So the person who wrote that letter critiquing Newton, and this is real, the person who wrote that letter so overtly critiquing Newton and wrote that letter to Bentley, the person who wrote the letter critiquing Newton that way was Newton. Newton wrote that letter, and he wasn't joking around. It was driving him crazy. He hated Newton hated his own theory. I mean, like for real. And I'm getting quiet now for real. I mean, this is one of my, but I'm not trying to trick you. Like, and Newton wasn't trying to trick anybody. He wasn't being falsely modest. That's why he privately wrote that letter to his mentor, Bentley. Like, it was meant to be a private letter, but then it was like published later on, like Good. I'm glad if your mind is blown. And listen, I mean, this is one of my favorite moments. I mean, this is why I love these guys so much. This drove Newton crazy to his dying day. Newton advanced the theory because it worked, because the numbers worked, because they made predictions that were verifiable and verified. But Newton hated the theory. He did not understand how it could possibly be true. In fact, he delayed publication of it for a while. For a while, it was just his own private craziness up in an attic that he was like confessing to. What Newton was saying, and this is really, you said before there's a fine line between physics and philosophy. There is, and there's a fine line between simple and hard. There's a fine line between genius and crazy too, and not for coincidental reasons. I mean, and this is the birth of modern science as we know it in a very deep way. Like, again, Newton wasn't even called a scientist. He wasn't called a physicist. He was called a natural philosopher, as was Galileo. All those guys, they were just thinking about everything. And then they were trying to think about certain things in certain ways. But what Galileo and Newton, how they changed the world. I mean, and of course you hear about them all the time, but I think I never understood how deep this went. Like the first 8,500 times I heard it in high school and college. The thing that Newton and Galileo were doing when they broke off from the rest of philosophers, they were actually coming up with a way. They were saying, look, at a certain point, we just have to look at what the world seems to be doing. We have to do reproducible experiments that get data that then, and we have to like come up with ways to get data that other people can get the same data and get the same results. And we have to look at this data and look at it seriously and look for models that describe this data so that we can predict things in the future. If we try to impose what we already think the universe is on our data or on our thoughts about the universe, then we're defeating the whole purpose. Then we're playing God, and we're not investigating. We're dogmatizing, or we're opinionizing, or whatever. The thing about Newton's theory is it is literally a description. What he did was he took all the numbers and put them together into math equations that generated more numbers. It's like one big computer program in a way that worked. I mean, it really works. I mean, it is really how we put a man on the, and we didn't put women yet, but how we put people on the moon. And I do believe we did, by the way, and I'm willing to believe a lot of conspiracy theories, I am, but I really do believe that we really did put people on the moon. And one of the reasons I believe that, and because I know you've heard the conspiracy theories and stuff like that, one of the reasons that I really do believe that we really did put people on the moon, even though I've heard a lot, I've taken very seriously a lot of the objections. I think a lot of the objections are very interesting. But one of the reasons, and believe me, I don't put it past I don't trust our government not to. I mean, I believe that our government could have conspired to make us believe that it absolutely was in our interest during the Cold War in fighting Russia. Like, I don't believe that our government was morally above. Well, okay, fair enough. That's a good reason right there, Gabriel. Right. But let me also just say, in case any of you think I'm crazy, I don't trust everything our government does just automatically, or NASA, just because they say it. But so do I believe that our government might have wanted to conspire to make us believe that if they could have? Sure. Like nobody's above anything. But here's the thing. The technology to have faked that is much like the technology required to put a person on the moon in 1969 was far more advanced than the technologically that would have been required to fake it. Like, we didn't have Adobe print shop then, to put it mildly. Like, we had missiles, we had that technology because we were in a freaking race to like actually win a war. Like, it all was part of it. Right. Right. Seriously. Okay, just 3D print a moon, easy. Right, but we couldn't do that then. Like, we literally had more advanced rocket technology than we did conspiratorial print technology, because one was an easy way to win a war and the other wasn't. Like, but anyway, so what I'm saying is we put a person on the moon, as far as I know. And we put a person on the moon in 1969, not with Einstein's equations, with Newton's equations. Like, Einstein was alive. We had Einstein. Everybody loved Einstein. And he had advanced the theory of gravitation to an even more sophisticated mathematical level. He had already won a Nobel Prize. He already had published general relativity in 1950. Like, the world and NASA and everybody had Einstein's equations for gravitation by 1969. But those are not the equations that we use to go to the moon. Right. That's what I'm trying to say. It was easier to put a person on the moon than to fake it. I really believe that. And I'm telling you that the equations and the concepts that were used to put a person on the moon were Newton's because they work that well. They predict that accurately. And that is why Newton believed. I mean, he didn't know about that, but he got all the orbits right and eclipses and all that right with his equations. So as a scientist, which didn't even exist barely at the time, it was just start. But the whole thing of science is that Galileo and Newton, who, but by the way, also both totally believe, and I'm not telling you what to believe, but believe me, they believed in the divine. They believed in the heavens and all of that. But in their point was they believed in powers greater than themselves so humbly, even as arrogant as they were so humble in the face of nature that they tried as hard as they could to come up with methods that would not be trusting their intuitions, but just be trusting what nature said to them. So, I mean, this is really the point of the scientific method. The scientific method is all about not trusting scientists. The scientific method is a method that scientists come up with because they're smart enough to know that they don't know what they don't know. So they try to come up with methods that are actually outsmart them so that even their tendency to lie to themselves or to believe what they want to believe can get checked and double checked and triple checked by the reproducible method and the separation of variables and all that. So Newton literally came up with an equation that seemed to describe all of this data that Copernicus had collected, that Kepler had collected, that Galileo had collected. Newton put all this data together in an equation that totally worked and works to this day and is powerful and allows for and produces technology and all this. But Newton could not understand how it could possibly make sense. It was assuming something about the universe that totally went against all of Newton's intuitions. I mean, because it basically implied that the information could travel across empty space like by itself at either infinite rates or finite rates. And Newton couldn't decide either one, which one. He ultimately actually decided that the information must travel at infinite rates. Newton ultimately came to the conclusion that the information must travel at infinite rates, which today we say is not the case. Like an Einstein says is not the case. So Newton knew he was on really thin ice with all of this, but that's not the equation. The point is that Newton had intuitions that said, this doesn't make any sense. This doesn't make any sense. This doesn't make any sense. I hate this. How could this be? How could this be? How could this be? But the scientist in him said, that doesn't matter. That's not what it's not about what I think makes sense. I'm here to find out what makes sense, not to impose what I think makes sense on the universe. So even his deepest intuitions, they troubled him so much that they drove him crazy, and they did. I mean, he went to his grave like a whirling dervish of a confused, angry person over this. And later in the letter, in other places, he actually publishes something that says later in the letter, he says, how gravity could possibly do this, I leave to my predecessors. I leave to my descendants to figure out. Like, he actually writes a challenge to future generations. Like, it's up to you guys to figure out how this could possibly be the case, because I don't get it at all. I hate it, but it seems to work. And it took until Einstein for someone to actually come up with an explanation for a complete explanation for how this works. But yeah, it was Newton who hated his own theory. And that's how deep the theory goes, and how deep Newton goes, or how deep thinking should go. And I like the fact, if you guys find that like weird, I'm glad. Like, I love to hate this idea myself, but that's how, I mean, science is just, it's not a cookbook. It's not a cookbook. It is it is a way of thinking and a way of life and all that. Now, what does this all have to do with the class? Well, I mean, hopefully a lot, but in particular, and I know we only have 10 minutes, but we have 8 minutes, but that's just enough for me to at least say this thing. So what I'm saying for the moment is Newton said action at a distance happens, and it happens in this mathematical way. And then Coulomb later said, yep, action at a distance happens between protons and electrons, and it happens in this mathematical way. Both of them basically put up their hands and said, I don't know how. I don't know why. I don't even like it. I mean, Coulomb wasn't as sort of violent about it as Newton, but both of them were like, I don't know. I'm just a scientist. I'm not a philosopher anymore. Like, I'm not God, and I'm not talking about God, and I don't know. I don't know why. I don't know how. I just know this. Apparently, this is what the data says. And that's my job as a scientist. That's my pay grade, is what the data says, right? And again, that's like a new job that just, it's only since Galileo do we even separate out these jobs like that. But so they say, here's the data, here's what's happening. Someone else is going to have to explain why or how or what the mechanism is. Now, in modern time, now it gets very modern in the 20th century with Einstein. It can get very, very crazy. But the basic modern idea that gets developed in the 19th century, particularly by a guy named Faraday, you may have heard of in other classes, the basic idea, the basic explanation, or not even explanation, the basic mechanism in which we believe, the mechanism or the method or the mode or the mechanism by virtue of which the description of one point in space can be accessed by any and every other point in space, the mechanism that allows for the transmission of information between points of space is called the field. That's what a field is, okay? Newton didn't know about fields. We developed, sorry. The answer is, and I know we have 5 minutes, but the answer to this question, the question of how the heck can this happen, the answer is the field, or our model, our way of talking about this is and the mathematics, the basic mathematics in a way are very easy. And I know we have 4 minutes. The mathematics are not the hard part. And I know I have 4 minutes. What I'm saying now, and this is not going to totally satisfy anybody, and it shouldn't totally satisfy you. This is not going to make you believe in fields, but this will make you understand what people mean by the word field and why they have the word. We used to say the sun exerts a gravitational force on the earth. A force is I pull you, like object number 1 pulls another object, or proton pulls electron. That's force, 2 objects interacting. But whenever it comes to interactions that are happening through space, because that causes so many mathematical and philosophical difficulties, like how does something pull on something else through space? Put another way, how do we send information through empty space? What we now say instead is we say the sun exerts a gravitational field in space. And then so the sun makes a field, whether or not the earth is there. In other words, it takes 2 objects to make a force, but it only takes 1 object to make a field. A field is all the information appertaining to a source. So if a gravitational force was M1 pulls M2 throughout R squared, the gravitational field is the gravitational force dividing out M2. The gravitational field created by the sun is G times the mass of the sun over R squared. And similarly with a proton and electron. In other words, we used to say object 1 pulls object 2, but then we realized it was doing that through empty space. So that's weird. So instead, what we now say is object 1 creates a field everywhere in space i.e. you could picture it, if you want to picture like a bunch of arrows everywhere in space, not literally arrows, but a bunch of little vectors everywhere in space, and every point in space, there's a number of newtons per, if we're talking about gravity, a number of newtons per kilogram waiting to happen. Like at this distance, there's a certain number of newtons that if I put on kilogram there, it will be pulled by those newtons. Let me say this all again. Instead of saying sun pulls earth, we now say sun creates field at every location in space. In other words, creates a number of newtons per kilogram with a certain magnitude and in a certain direction. And if the earth gets placed at one of those objects, then it will be pulled by the field. So I don't pull you, I create field, and then the field pulls you, is what we now say. In other words, a field is like a medium. It's an agent between the two objects that must exist and does exist whenever we're talking about action at a distance. What is it? Is it really a physical object? No. What it is the information of the first object sitting there. In other words, the sun is at all times sending out a little encoding or a little bits or whatever, saying precisely how massive it is and precisely where it is to every location in space. The information is just sitting there everywhere in space. And then when the Earth comes along into space, it is dunked in that field of information, and the field pulls it towards the sun. Still doesn't answer all the questions at all, but it's kind of like the word God. It doesn't answer, but it's just a word. I shouldn't say that. It's like the label X. The word field is a word now for what must be happening somehow. There's got to be some mechanism. There's some way that the information of the sun travels to the earth, or the information, and I see that it's 710, or the information of the earth travels to the sun, or the information of an electron travels to a proton. What we say is there's a field everywhere in space containing this information, and the way information is sent back and forth between objects is via ripples through this field. The field is like a medium, and when we send information through it, it's like sending ripples through the medium, like sending wave pulses through the medium. The medium is immaterial, and I'm not saying that by giving it a word, I've explained everything at all. I haven't. I'm just saying the word for the fact that something is going on in between objects, the word for that is field. So I exert a force on you. But if it's action at a distance, then we say, I exert a field, and the field exerts a force on you. The field is the middle agent that contains and transmits the information from one point in space to another. That's what a field is. It's the ultimate unthingy thing. But I know it's 7-11 now. You guys have been very, very patient. I don't know if that was too much or too little or whatever, but that's the deal. And we'll talk fully about the final exam, put this all together next Monday, but you'll talk with Joe. And okay, thank you very much. Have a great week. Thank you. Oh, cool. Okay, I'm just going to, oh, awesome. Awesome. Oh, cool. Right. No, I love what's happening in the chat. Thank you guys very much. I'm just staying here and reading the chat, but you're good. I mean, I'm good. Thank you guys so much. Have an awesome week. Thank you. Thank you. But that's great. That's great, Harry. Seriously. All of you. That's great. And thank you. A lot of you participated a lot. So thank you. Thank you. And I totally notice. Thank you. All right. Awesome. Goodbye. Good.